All right, continuing with the third video here for section 6.3. We've been talking about binomial random variables, how to calculate the probabilities of binomial random variables. We're going to take a look here today at a couple of formulas that are actually on your formula sheet, and this is for how to calculate the mean and how to calculate the standard deviation of a binomial random variable. Okay. So once again, these are both actually on the formula sheet, but you'll notice here that how to get the mean of a binomial random variable. So this would be like the average number of whatever your random variable is. You would take the number of trials, okay, n is the number of trials, and you would multiply that by the probability of a success. And when we look at an example, this formula really makes sense why this is the formula here, and that'll come to light in an example here. Okay, the other formula that is actually on the formula sheet is how to find the standard deviation of a binomial random variable. Okay, again, this n is representing the number of trials. The p is the probability of a success. And then you'll notice the 1 minus p is actually the complement there, the probability of a failure. Okay. Now, these come with interpretations. So when you have your expected value or your mean for your binomial random variable, it's very important to make sure that you're saying that this would have to happen over repeated trials, okay, like over many, many times here. The average number of, and then you'd fill in the context of your random variable would be about, and then you'd fill in the value of the mean, okay? In terms of the interpretation for the standard deviation of a random variable, okay, you'll notice this really follows a lot of the format of how we describe just a standard deviation in general. The number of, and then you fill in the context of your random variable, would typically vary by, then you would put the value of the standard deviation there from the mean of, and then you'd put the value of the mean. Okay. Something that is very important is that these two formulas up above here, they only apply to binomial distributions. You cannot use these formulas to find the average and standard deviation of any other distribution unless it is binomial. Okay. All right, so let's go ahead and take a look at this example here, talking about kind of taste testing soda here. It says the makers of a Diet Cola claim that its taste is indistinguishable from the full calorie version of the same cola. To investigate, an AP statistics student prepared small samples of each type of soda in identical cups. Then she had volunteers taste each cola in a random order and had them try to identify which was the Diet Cola and which was the regular cola. Now here's the results. Overall, 23 of the 30 subjects actually made the correct identification. Okay, that kind of feels like that's a lot. Out of 30, that 23 of them were able to distinguish which one was the diet and which one was the regular cola. So it says here, if we assume that the volunteers really could not taste the difference, but rather that each one was just guessing, okay, with a 50% chance of being correct, okay? Either it's the diet or it's the regular. We're going to let X be the number of volunteers who correctly identified the cola under the assumption that they really couldn't taste the difference. They were just guessing what the cola was. Okay, so the first question here is to find the mean and the standard deviation. Okay, please keep in mind that even though this section is all based on binomial random variables, if this was something on the AP test, you would need to make sure that you were confirming that this is actually a binomial random variable before you would use the formulas for mean and standard deviation. Okay, so we're going to call a success, really a success is looking back at what we're defining our random variable to be, and that would be a correct identification. Okay, so a success is a correct identification, and a failure would be an incorrect identification. Okay, in terms of the independence, I'm just going to make a statement here that we're just going to assume that each identification is independent of the next. Okay. Okay, the number of trials here, it says that there were 30 subjects, so that is the number of trials, and the probability of successfully or correctly identifying the colas, now look back here, it says under the assumption that they actually couldn't taste the difference, we're just assuming that they are guessing. It's like a 50-50 chance that they would guess it right. So the probability of a correct identification would simply just be a 1/2. Okay, it meets all the criteria there for being a binomial random variable, so we can proceed with using those formulas that are up above there. Okay, now here's where I was saying this formula actually makes sense. When we're looking for the mean, this is like what would be the expected number of correct identifications that we think would happen out of 30 if there was really just a 50-50 chance of guessing it correctly. And you know, when it's posed like that, well, we would expect half of the 30 to guess correctly. We'd expect there to be 15 correct guesses. And that's in fact what this formula is suggesting. You would plug in the number of trials, the 30, you would multiply it by whatever the probability of your success is, and that's going to give you the correct proportion out of that total number of trials that you would expect to be in a success. Okay, and so obviously we would expect 15 correct identifications. Okay, when it comes to our formula for the standard deviation, it's the square root of the number of trials times the probability of a success times the probability of a failure. Okay, this is what we're getting for our standard deviation. Now you can see those templates up above on your paper there, but we're asked in part B to interpret, always in context, both the mean and the standard deviation. Okay, so for the mean, we would want to say something like over repeated trials, the average number of correct identifications would be about 15. Okay, that is the interpretation for the mean. For the standard deviation, we can say the number of correct identifications will typically vary by about 2.74 from the mean of 15. Okay, that would be the correct interpretation for that. Okay, let's look at part C here. It says in part C, of the 30 volunteers, 23 made correct identifications. Now the question is, does this give convincing evidence that the volunteers can taste the difference between diet and regular colas? Because keep in mind, we were actually only expecting about 15 of the 30 to correctly identify. If they were guessing, that's how many we would expect. But we got a significant amount more than just 15. We got 23. And so we're just wondering, is there enough evidence here based on these results for us to say that, you know what, maybe these volunteers weren't just guessing, but they actually could maybe taste a difference, and that's why we had so many correct identifications. Okay, so we know this is a binomial random variable, so we just want to see what is the probability that there could have been 23 correct identifications out of the 30. Now, if we were going to use the formula for this, and this would be the formula on the formula sheet, okay, and you could pull that formula sheet out or flip back a few pages here at the beginning of this notes packet here and see that the way this works is it's an n here for the number of trials, the x, the probability that we're trying to find x successes, probability of a success raised to an exponent of that many successes times the probability of a failure with the remaining amount that would be failures. These always have to add up to the total number of trials. Okay? Or we could calculate this same probability using the calculator command. Binom has to be, though, PDF. Okay, again, 3 inputs, number of trials, probability of a success, and then looking for the probability of that many successes, which is 23. Okay, whichever way we do this, we end up getting an answer of 0.0019. Okay, and so here's the number that we're looking for. Okay, we want to look at that number. Remember, 5% is our benchmark in statistics to kind of see how likely it is that something could happen. When it's under 5%, then it's not very likely that that could have occurred just by chance. Okay, so we're going to say it is unlikely by just guessing, because if they're just guessing, we're leaving it up to kind of random chance here, that 23 of the 30 correctly identified the cola. Okay, and then I'm just going to put in the parentheses here what that percentage is. It's not even 1%. It's 0.19%. Okay, very unlikely chance. And so I'm just going to say, because this is less than 5%, there's our benchmark, this is providing convincing evidence that they could taste a difference. Okay. So we're saying, look, it's really, really unlikely that just by guessing, the odds of just by guessing 50-50, that you would get 23 out of 30 to have guessed it correctly is roughly a 0.19% chance. That is extremely unlikely that that could have happened. And so since we had so many correctly identify it, we're going to call that is majorly convincing evidence that it is more likely to believe that they could, in fact, actually taste a difference between these two sodas. And that's what was accounting for such a dramatically high number of correct identifications. Okay, in number 7 here, it says find the mean and the standard deviation of the binomial random variable x. And the parameters are the number of trials is 21 and the probability of a success is 1/3. Okay, we don't have a lot of context here. They are not asking us to interpret this. I think they're just wanting us to get comfortable with the formula. Okay, the formula would be n times p. You can see that there. So we would expect over repeated trials, whatever it is that we're talking about here, we would expect that, that would occur about 7 times. And then our formula for standard deviation, number of trials times number or probability of success times probability of a failure. So multiplying by 1/3 and then 2/3, and 2.16 is what we're typically saying that this particular random variable would vary from the mean of 7. Okay, moving on here to the next page, we're talking about blood types. It says each child of a particular pair of parents has a probability of having type O blood. It has a 25% probability of having type O blood. Genetics says that children receive their genes from each of their parents independently. Now that's an important thing here, because when I come down to try to determine independence to whether this is a binomial random variable, I want to keep that in mind. It says if these parents have 5 children. Okay, I'm going to go ahead and just kind of fill some of this in as I'm reading it here. So 5 children, that would be n, the number of trials. I'm going to go ahead and say that the independence condition is met because I'm just going to say genes given independently. Okay. It says the count X of children with type O blood is a binomial random variable with n equal 5 trials, probability of a success, that's the 25%, okay? So a success is defined as having type O blood and a failure is not type O blood. Okay, so we've definitely clarified this. It kind of mentioned there in the problem that this was a binomial random variable. It says here, in this setting, a child with type O blood is a success, we defined that there, and a child with another blood type is a failure. Now here's the question. What is the probability that 2 of the 5 children from a set of parents would have type O blood? Okay, so we're going to do this problem two different ways here. We're going to take a look at, or we're just going to do it using the calculator rather, excuse me. Okay, now this is an equal to problem. We're looking for the probability that exactly 2 of the children out of the 5 would have type O blood. So this is going to give us an opportunity to use the binomial PDF, okay, with our 3 inputs of 5 trials, probability of a success 25%, and then the number of successes that we're after is 2. Okay, we would type that in, and we're looking at roughly 26.37% is the likelihood here. So we could draw our conclusion that in context here, the probability of 2 of the 5 children having type O blood is 26.37%. Okay, on the next page here, this is just piggybacking off of that exact same example that we had just looked at. It is mentioning here that we've already checked these conditions here, so we're not going to go back through and check the bins condition again, but it says each child, keep in mind, has a probability of 25% of having type O blood, and we're still talking about 5 children in a family. Now we want to find the probability that exactly 3 children have type O blood. Okay. Once again, always be comfortable, familiar with how to use the formula. It does creep up in many multiple choice questions, so you want to be comfortable with how it's set up: number of trials, number of successes, probability of a success raised to the number of successes times the probability of a failure raised to the number of failures. Okay, or we could do binom PDF. We're looking at 5.25 and 3. Okay, either way, we're getting 8.79% chance there. Okay. Okay, I'm just going to draw your attention to this problem here at the bottom, which I already have filled in here for you. Now, this is a little bit different. It says, should the parents be surprised if more than 3 of their children have type O blood? When they ask you this question about being surprised, you need to find the probability of what it's set up here, and then see if that probability is above 5% or under 5%. And so there are 2 ways to do this. If we're talking about more than 3 out of the 5, we're talking about 4 children having type O blood, and then all 5 children having type O blood. So your options are, you could use the formula twice and add those 2 probabilities together, or you could use binomial CDF. Now here's where you have to be careful. It says more than 3. Okay, when it says more than 3, that's not greater than or equal to, it's only greater than 3. So if we're going to use the CDF feature, remember, CDF only works for a less than or equal to. Okay, so whatever number you're putting in this spot here, you are including everything from 0 up to that number in your probability. Okay, well, if we want everything greater than 3, then what we don't want to count, and this is why we're subtracting it off of 1, is we don't want to count everything from 0 up to 3. That's why I've included the 3 here. We could type this in the calculator. You can see that we get the exact same answer. We're going to respond that there is only a 1.56% chance that more than 3 of the children would have type O blood. And then we want to add this because it was asking, should they be surprised? Since this is less than 5%, this is surprising. Anything under 5% is always surprising if it happens, because the likelihood of that occurring is just considered extremely rare if it's under that 5% benchmark. Okay, the last page is where we're going to wrap up here, and this next page is going to kind of tie in one other really important condition. In the previous video, we had learned about the 10% condition, and next here we're going to learn about something called a large counts condition. It says binomial distributions, something really interesting happens as your sample size gets larger. Okay, what you'll notice happens to the shape of the binomial distribution, you can kind of see this happening in these graphics here. As your sample size gets larger, you'll notice that the distribution feels like it becomes more and more of a normal distribution. Okay, we had used that normal CDF feature a lot back in chapter 2, where we did our lower bound and our upper bound, our mean and our standard deviation. It's a great calculator command to calculate probabilities. Now, binomial distributions have their own calculator command. However, if your sample size is large enough, then that means even a binomial distribution, you could calculate the probability using normal CDF. So let's talk through how large your sample size would have to be in order for it to be considered then a normal distribution. Okay, this large counts condition allows you to use the normal approximation or normal calculations for a binomial distribution. Okay, here's how this is going to work. Okay, I'm going to go ahead and fill in here what we are used to. When we did normal CDF, we had 4 calculator inputs. We always had the lower bound, the upper bound. Okay, and if we find that the sample size is in fact large enough, and I'll show you what that is here in a moment, you would then take the mean of the binomial distribution, you would fill that in to the third blank where we always put what the mean was, and then you would fill in the standard deviation of the binomial distribution in the fourth blank. Okay, so how large does a sample have to be? Well, the sample size has to be so large that if you took the number of expected successes and the number of expected failures, both of those number of expected successes and number of expected failures have to be at least 10, okay? And that's what this formula is showing you. Remember, n times p, that's actually just the average, what you're expecting the number of successes to be. So if you take n times p, and it is going to be greater than or equal to 10. That's representing the number of expected successes, and then also the number of expected failures. So n times 1 minus p also has to be greater than or equal to 10. If both of those are at least 10, then it meets this what's called large counts condition and allows you to use the normal distribution calculations. Okay, so let's put this in action with one problem here, talking about a survey done with people's attitudes towards shopping. It says sample surveys show that fewer people have been enjoying shopping than in the past. A survey asked a nationwide random sample of 2,500 adults if they agreed or disagreed that, quote, I like buying new clothes, but shopping is often frustrating and time-consuming. So we're going to assume that 60% of all adult U.S. residents would say that they agree with that statement if they were asked the same question. We're going to let X, that's our random variable, represent the number in the sample who agree. And we are asked to calculate the probability that 1,520 people out of the 2,500 adults surveyed or more would agree with this sample. Okay, so before we calculate that probability, I'm going to go ahead and see if this meets the binomial conditions here. Okay, so success would be that someone agrees, and a failure would be that they disagree. Okay, now keep in mind, when they are selecting these individuals to survey, they don't want to survey the same person twice. Okay, so this represents sampling without replacement. Okay, they don't want to throw that person back in the poll and select them again. All right, so since it's without replacement, I have to be really careful with this independence condition. I need to make sure that in order for the independence condition to still be met, I have to show that the 10% condition is met. Okay, remember that's making sure that our sample size is no more like 10 times our sample size is still less than or equal to our population size, okay? So you have to show 10 times. Remember, our sample is the 2,500 adults. Now, I don't know how many adults there are in the U.S., but I'm going to just write the word all U.S. adults. I think that it is certainly safe to assume that 25,000 is less than all the U.S. adults that we have in our country. So we're going to say that that definitely meets that 10% condition, which means it meets the independence condition. Okay, the number of trials is the number in the sample, 2,500, and the probability of a success is 60%, because they told us back here that we're going to suppose that 60% of U.S. adults would say that they agree. Okay. All right, so we are asked to estimate the probability that in our sample of 2,500 adults, that 1,520 of them would agree with the statement. Okay, now keep in mind, this is a greater than or equal to. So if I'm going to do a binomial calculation, I need to use the complement here and do 1 minus binom CDF. Now I want to think through here. Okay, I know that my sample size is 2,500. Probability of success is 60%, but I'm wanting to include 1,520. So what I'm wanting to subtract off is anything from 0 up to 1,519. Okay, that's what I want to subtract off. And that would give me a 21.31% likelihood. Now, that was fine to do the problem using binomial calculations, but what we're going to do now is check that large counts condition and show how we could also get the same answer by maybe using normal CDF. When it says to test for normal conditions, this is, and I'm abbreviating here, LCC is short for the large counts condition. What you have to show is you have to show that the number of successes and the number of failures are both greater than or equal to 10. So keep in mind, again, this is number of successes, and this represents the expected number of failures. Okay. Now, when you do this on the AP test, you don't have to show these formulas that I just put there, but you do have to show, and I'm just going to, I'll replace standard deviation down here, okay, just so I have a little bit more room here. You have to show your substitutions into that formula. Okay, so N is 2,500, P is 0.6. Okay, and I have to show that that's greater than or equal to 10. I'm going to multiply that left side. Absolutely, 1,500 is greater than or equal to 10. And then over here, I'm going to do the same thing, except the probability of a failure would be 40%. Okay, and then again, that is checking out fine there. Okay, so that means this sample size was large enough that I absolutely can use normal conditions here. Okay, so I'm going to do the expected number of successes here, which is my mean, 1,500, and then I'm going to do the standard deviation. Okay, these formulas here were up above here on the other page. Okay, these are on the formula sheet, by the way. Okay, standard deviation, 24.49. Okay, so we've established that the conditions are normal, so that means I can kind of abbreviate this all together. I'm using my N for normal. Okay, remember this is our mean, and that's our standard deviation. Okay, so to calculate this answer, probability that X is greater than or equal to 1,520, I can do normal CDF. I'll label my inputs, lower bound, upper bound, mean, and standard deviation. 1,520 up to 10,000. 1,500 is the mean. 24.49 is the standard deviation. My answer, 20.71%. Okay, not exactly the same as what we got when we did binomial CDF, but on an AP test, they would accept you doing the problem this way or you doing the problem the other way. They would accept on the rubric, it would show both of those answers for sure. Okay, all right, that is a good place for us to stop on this video. We will pick up in the next